Okay, in this next lecture section, we're going to talk about what is the input impedance in general for any arbitrary resistor. And it'll be very easy to then expand that to any arbitrary load with capacitors and inductors as well. All right, so let me remind you of the definition of an input impedance. It equals V in plus V out. These are all phasors, divided by I in plus I out. Again, phasors. And the setup is we have a transmission line. This transmission line has intrinsic impedance Z0. And it's going to have some unknown load here. And this transmission line has a length of D. Okay, so what is different about this scenario compared to the DC case is that we know what V out is if we know what V in. So let's try to write what V out is as a function of V in. All right, so let's start out V out. We're going to start out with our input voltage phasor. And the first thing we want to do is we want to propagate that input voltage to the load. Right? So here is V in coming this way, and here is V out. You want to know what these phasor values are. So first we want to propagate it to the load. And this is a wave that's propagating in the positive direction. And let's define this axis as our Z direction. Let me move this a little bit. Probably a fast way to do that. Nonetheless. All right, so V out as a phasor will be V in times a phasor. Let's start by adjusting the phasor value in order to propagate to the load. All right, so that's going to be multiplying it by E to the minus J times beta times D. All right, all we've done is we've rotated the phasor in the clockwise direction by an angle of beta D, because that's how many wavelengths we've moved, or how many radians we've accounted for by moving downstream in the direction of propagation. Now, once this wave hits the load, it's going to reflect, right? So whatever that phasor value is striking the load, it's going to reflect, and it's going to multiply by gamma L. So I'm going to now multiply this by a gamma L to account for the reflection at the load, right? Once that phasor value has reflected from the load, it now has to propagate back out again. And in this case, D is now moving in the opposite direction, is moving in the negative Z direction, but the wave propagation is e to the positive J beta Z instead of negative. And so we end up with the same multiplication again, minus J beta, sorry, not a Z, that's a D. Okay, and now we've completed everything. We've basically figured out what the phasor value of the emerging voltage is as a function of the incoming phasor, simply by propagating it to the end, reflecting, and propagating it back out. We, of course, can combine these e to the minus J beta D terms, and we get this. V in times gamma L times e to the minus 2 J beta D. Okay, so that's voltage. Let's do the same thing with current now. All right. I out. We'll start out by taking the I out will be equal to the input voltage divided by Z0, right? Z0 is still going to define the ratio of voltage to current for any wave that's moving all along this transmission line. We still have to propagate it to the load. We're going to have that same phase factor of e to the minus J beta D. But now we get to the reflection, okay? And the reflection for current is the negative value of the reflection coefficient for voltage. So I'm going to put in a minus gamma L right there to indicate that we're multiplying this result by minus gamma L. And then we got to propagate it again back to the source. So we're going to do a minus E, J to the minus E, E to the minus J beta D, combine the two exponentials together, and this will be V in as a phasor divided by Z0. I'll put a negative sign right here. Gamma L e to the minus 2j beta d. All right, so now that we have defined the output current and voltage, we can now rewrite the input impedance. So Zn works out to be Vn over Zn, sorry, Vn over In times 1 plus gamma L e to the minus j 2 beta d divided by 1 minus gamma L e to the minus j 2 beta d. All right, so now we have the input impedance. All we need to know is the length of the transmission line and something about the reflection coefficient at the load, and we've got this input impedance here. All right, now Vn over In, we can replace that. We have a much more convenient description of what that is. That is simply Z0. So let's rewrite that. All right, now you can do some math on this, and I'm not going to go through it, but if you do a little more math on it, you get a slightly different expression, which is more common, and I'm going to write that in. I wouldn't say you have to measure, you have to memorize this, but you may be using it often enough that you probably will end up measuring it. So Zn, the input impedance of this transmission line, a length d away from the load, can be written as Z0 times the load impedance plus j Z0 times tangent of beta d divided by Z0 plus JZL tangent of beta d. Right, that this is equivalent to what I wrote before. There's a little bit of mathematical manipulation that I haven't shown. All right, now this is the input impedance of any transmission line. Again, AC signals are on it, so we assume everything is sinusoidally varying, and we're assuming that you're taking that input impedance at a distance v away from the load. All right, so this is the in, sometimes written like this. It's the input impedance specifically at a distance d from the load. All right, a couple of sanity checks, which you can verify yourself. If d equals 0, then the input impedance works out to be ZL. That should make perfect sense. If there is no transmission line, then the input impedance should be exactly the same as the load impedance. Beautiful. That's good to know. All right. If ZL equals 0, if we have a load that is a short circuit, then Zn works out to be J times Z0 times tangent of beta d, which is good. That's what we covered in the last lecture. Nice to know that it hasn't been broken. And finally, if the load impedance equals infinity, plug that in and solve, you end up with Zn equals minus J times Z0 times the cotangent of beta d, again, matching what we figured in the previous lecture. So that's all good. This seems to be a more generalized version of the open and short circuit cases that we considered earlier. And in fact, we've actually unified them. All right. Now there's a very special case that I do want to talk about, which is the case where d equals lambda over 4 is equal to exactly a quarter wavelength. When we talked about open and short circuit cases, the quarter wavelength point was when they flipped around. An open circuit appeared to be a short circuit, and a short circuit on the load appeared to look like an open circuit. If you plug in d equals lambda over 4, in which case beta d equals 2 pi over lambda times lambda over 4, which is 1/2 pi, plug all that in, you end up with Zn equals Z0 squared over ZL. All right, specifically for D equals lambda over 4, the quarter wavelength point. All right, so I want you to remember that one. This one is definitely worth memorizing. That at the quarter wavelength point, you have this sort of magical inversion of Zn. I'm going to show you a minute what exactly this means. Is Z squared over ZL. But I'm going to give you one more thing, which is Zn again equals ZL for D equals lambda over 2. Right, at the half wavelength point, you're back to where you were at D equals 0. In other words, it's just as if you have the load there. And we'll see that a little bit more in a second. All right, so let's first consider the special case of specifically resistively loaded lines. All right, so let me show you a couple plots here. Okay, so there are two plots here, two plots to this, left and right. The left side is the real part of the input impedance, and the right side is the imaginary part of the input impedance, just using that formula that I just showed you, the one with the tangents in it. And so for a short-circuited load, and that's the case where ZL equals 0 ohms, there is no real part ever, because it's a purely imaginary number. So on the left side, everything is 0. The right side, the imaginary part, we have this repetitive pattern. We plotted it in the last lecture. It wraps around every half a wavelength and repeats. And at the quarter wavelength point, everything inverts. So a short circuit becomes an open circuit at a quarter wavelength. And at a half wavelength, it returns to being a short circuit. Process repeats. For the first quarter wavelength, this is a positive imaginary impedance, which is another way of saying it's inductive. And for the second quarter wavelength, it has a negative imaginary impedance, which is to say that it is capacitive. All right, let me add one more on top of this, which is a perfect match, right? That's a case where the impedance of the load is precisely the same as the intrinsic impedance of the transmission line. If that's the case, then we have a perfect match. There's nothing is reflected. The real part of Zn turns out to be Z0, right? This value here is normalized to Z0, so it's 1, right? Which is to say that Zn equals Z0 at all locations is exactly the same, because there is nothing reflecting, nothing to sort of modulate that that standing wave ratio pattern. The imaginary part of Zn is also 0 as well. All right, now I'm going to add another one to this, which is something in between a perfect match and a short circuit. And it's actually going to be a load resistor that is half the value of the transmission line impedance, right? So for example, this is the Win TLS case we covered, where you've got a short circuited load, and you've got a 50 ohm match load. And if you put in 25 ohms, that would be the case where the line is double the load. And so that is shown in the yellowish line. Now, the real part you can see is oscillating back and forth between two values. There is a minimum at the load, and there is a maximum at when you're a quarter wavelength away from the load, and then it oscillates back and forth, right? So here, the minimum on the left, this is at the load here, and this is increase and decrease, and it oscillates back and forth. It repeats every half a wavelength. Right, there's a similar pattern on the right where the orange is kind of in between the blue and the maroon, where there is kind of a repetitive pattern. There is this sort of inductive first and then capacitive and then repeats, but it's not as intense, it's not as steep as the blue curve, right? So we are seeing something that's a little bit in between the two. All right, let me add one more to this, which is something that's in between ZL equals 0.5 Z0 and ZL equals Z0 exactly, right? So it's a better match than the yellow case, but it's still not a perfect match. And here you can sort of see the intensity of this oscillation is starting to reduce a little bit. We're getting closer to that perfect match. And that's true for both the real and imaginary parts. All right. Now, the reason why, in the case, let me back up here. The reason why the real part starts out as a low number and becomes a higher number, The reason it starts out as a low number is because we have a load resistance which is less than our line, because we're closer to being the short circuit. At a short circuit, we don't like to have voltage, but it's okay to have current. And that sort of feels like a low resistance or low impedance if you have no voltage but lots of current. And so the opposite happens when you go to a quarter wavelength. All right, so let's now take a look at something a little bit different. A second. Okay. So here again, we're going to do the same thing except with an open circuit now. Okay, this is the case where the load is an open circuit. And so again, we have the same characteristic. There is no real part to the input impedance. It's purely imaginary. And the imaginary part has this repetitive pattern that wraps around every half a wavelength. And after a quarter wavelength, the open circuit appears to be a short circuit. And then it repeats. The first quarter wavelength, we have a capacitive impedance. And the second quarter wavelength, we have an inductive impedance, right? Negative and positive values, respectively. All right, again, here's the perfectly matched case, same as before. The real part of Zn is precisely equal to Z0, and there is no imaginary part. And all this just comes from plugging things into that equation that I just gave you, that long equation. Just trying to give you the intuition of how this evolves. All right, and here is something in between. This is a case where ZL, the load resistance, is double the value of the line resistance. And here again, this nice repetitive pattern, it goes from a value of double the line impedance to 1/2, to double to 1/2 and back and forth. Now you might be saying to yourself, hey, it goes from a factor of 2 bigger to a factor of 2 less on the real side. Is that a coincidence? And the answer is no, it's not. That it's always going to be, it's going to oscillate between A and 1/A times your value of Z0. So for example, if ZL were something different, like 5 times Z0, then the real part of the imaginary, the real part of Zn is going to oscillate between 5 and 1/5, 5 and 1/5, compared to Z0, meaning it will be 5 times Z0, and then it will drop down to being 1/5 of Z0. And then it jumps up to 5 times Z0, and then it drops to 1/5 of Z0, and that pattern repeats. And a similar thing is going on in the imaginary component, where it starts out at being exactly 0. It becomes it becomes capacitive. At the quarter wavelength point, it goes back to 0, becomes inductive, and then returns again to 0, and the process repeats. All right. Here you can sort of see the resistive and reactive part, or the imaginary part, as a function of distance from the load. In this perspective, the load is at the end, and going to the left is walking away from the load. And the red and the green are the 2 cases where the load is either double or 1/2 the value of the transmission line impedance. And what you'll notice is that these look exactly the same. The only difference is that they are shifted by a quarter wavelength with respect to each other. That's very much like the open and short circuit cases, which basically had the exact same behavior. It's just a question of where you start along this repeating pattern. All right. But in that sense, there's something identical about having a load resistance that's double the line impedance or 1/2, right? Times 2 or divided by 2 pretty much are the same thing. And so that ratio of load to line is kind of like a measure of the quality of the match. So for that reason, let me go back to a plot of standing wave ratio as a function of the ratio of Zn over Z0, plotted logarithmically. And what you'll notice is that this 0.5 and minus 0.5 basically correspond to the same ratio of Zn to Z0. They're just opposites of each other. One has a ratio of 4, the other has a ratio of 1/4. And so what you'll notice is that this is perfectly symmetric around that, point where they are even, right? This point 0, that's where Zn equals Z0, because that ratio is 1, right? So in that sense, the standing wave ratio is sort of like a measure of the quality of the match, where having a line resistance that's 1/10 of the load resistance is the same as having a line that's 10 times the value of the load resistance. All right. You'll also notice that the half wave point right here, this is 0, this is the half wave point, always returns to where you started. So having a half wavelength of transmission line is basically the same as having no transmission line at all. Again, if you're considering one frequency. So with that, we can conclude we've sort of generalized the ability to characterize the voltages and currents on the transmission lines for any resistor value. And if we know basically what the ratio of the load resistance to the line impedance, that sort of gives us the characteristics that are going to appear in our line. The standing wave ratio, the input impedance is a function of length, the quarter wave point, all those things. In the next portion, we're going to talk about arbitrary loads where we have some combination of resistors and capacitors.